there you go. Start recording now. A point, as I said, it's just literally a pinpoint. It's the location. It has no dimensions. We'd say it's zero dimensional. Right? And then a line, you take 2 points and connect the dots. That's a line. It's one dimensional. Right? And so the dimension, as I said, corresponds to the idea that you can measure it almost. Like there's no measurements for this point, so it's zero dimensional. The line has length, so we say it's one dimensional. And just to be complete, the line segment would just be like something like this. So it's just between 2 points. So maybe I call the point A, point B. Right, and so it ends basically. It's this distance, whereas a line itself goes off infinitely in both directions. Right, and a line segment would also be one-dimensional, but that's just kind of an aside. All right, so just keep this in mind. And now let's go to planes. Oh, I guess so. If a line bends, it's called a curve. Right, a curve it's just any kind of. If you take your pen and draw some shape on your paper, it's going to be a curve. But we don't really talk as much about curves. All right, so a plane is an infinitely thin flat surface. So think of it as a sheet of paper that is infinitely thin, but the takeaway is that a plane has length and width, right? So in contrast to a line, which just has length, a plane has 2 things you can measure, a length and a width. So it's 2-dimensional. All right, so if I go back to my sheet over here, so let's see, we got a point, 0-dimensional, a line, 1-dimensional, and a plane. And so, I don't know, move it down a little. There you go, a plane that's 2-dimensional. And so a plane, it's a little harder to draw, but as I said, just think of it like an infinitely extended sheet of paper that's arbitrarily flat. So like something like this maybe. But again, there's no boundaries. So think of this in like 3-dimensional space, or you can just think of it as a flat sheet of paper on your desk. And so there's, infinitely many points on it. You have many lines going through it, and it extends out in all directions. It extends out this way, it extends out that way, frontwards and to the left as well. Right? Any questions? So if I say something's like 2-dimensional or 1-dimensional, I mean it's either like a line or like a plane, essentially. Right? Cool. Back to the notes. All right, so we got everything here. So the only reason we need these definitions really is because we want to talk about we want to talk about perimeter, we want to talk about area, we want to talk about volume. Those are the 3 kind of main topics we'll talk about in the geometry section here. We'll do some triangle stuff too. Not as much as you do in like a trig course, obviously, but we'll talk about triangles with a focus on their geometry. Okay. So the perimeter. Okay, so again, 2-dimensional shape. Right, so when we talk about perimeter, you can think of it as, you can take the perimeter of anything really that lives kind of in a plane, a 2-dimensional plane. So it's gonna be the shape, is the distance around the shape, right? And we'll do perimeters of various things, a lot of polygons. And a polygon is a 2-dimensional shape made of straight lines, right? And so the reason it's nice to find perimeters of polygons is just because straight lines are easy to measure, right? But again, perimeter you can find for any closed shape in like a plane. And closed, where's that? Polygon. Polygon. So closed just means the ends meet, right? So let me make a little note here. So if I have, so this is like a note. So if I have like this is not closed, right? Because the ends don't meet. Right? Now, on the other hand, if I have something like, this is closed. Right? Basically, it's just a matter of, do the ends meet? right? And you could talk about you could kind of talk about the perimeter of this shape. You wouldn't call it the perimeter. You just call it like the length of this curve. Usually perimeter we usually just we take to mean the closed shape. Just but theoretically there's no reason why I guess you couldn't take it to mean both, but we'll always talk about it in the context of a closed shape. Right? Anyway, let's do some examples. You've probably seen perimeter. Most of you probably know what it is anyway, just implicitly from daily life. But let's find the perimeters of these polygons. And you know these are polygons, right? Because they're closed two-dimensional shapes with straight sides. So all the sides, even though my drawings are a little sketchy, all the sides are meant to be straight. That is to say, lines or line segments, and they make like a solid. Like if you were inside this object, you couldn't get out without going over the line, right? Anyway, how would I find the perimeter of this object, this polygon?
You add up everything?
Yeah, you just add them up, right? So, and you know, one thing to keep in mind is note the units, right? So these are all centimeters. So I'll just add them up. Add up length of all sides. Right, so what do I get? 2 and 3 plus 2 and 1.5, and then 1.5 and 1. All right, so what is that? That's 3, that's 10, 11, I think. So I get 11 centimeters. And as I said, units, like centimeters, meters, feet, years, all that stuff. Units will be something we talk about next unit, but we'll use them here because, I mean, we're not going to do anything fancy with them right now. But right. Next one. So again, this is a polygon. It has all sides made out of lines. And these are just random examples I made up, so there's nothing special about this. It kind of looks like a hammer. But just like we did before, we just add up all the sides to find the perimeter, right? So you just go around and add them. There's no right or wrong order. So I'll start here and kind of work around. So 1, and you could put the inches in, but I'm just going to leave them out because I'm lazy. So 1 plus 4 plus 0.1 plus 0.1 plus 1.2 plus 1 plus 1 plus 3. All right, what is that? So I get 5, and then 1.4, and then 5. I think so. 11.4 inches. Oh, sorry about that. Kind of off the page. Yeah, you could also use a calculator, of course, to just add those up. But you can also do it in your head. Why not? Any questions about perimeters? Like most of you probably have seen these things. They'll get more complicated. All right. So we have perimeter, and as I said, the other kind of topics we want to talk about are area and volume. Volume we won't do today, I don't think, but we will do area. So the area, it's kind of silly. I put a blank there. Just I don't know. The area of a two-dimensional figure is the amount of surface the shape covers. Fine, right? And you know, two-dimensional figure. You could put closed there.
Your paper muted for me.
My paper?
Or didn't mute. It stopped. Like your paper is still stuck on the other one. Like it hasn't moved.
Oh no. Is it better now? Wait, let me switch.
Nope.
Oh, how about that?
Nope.
Oh no.
It's still just in the background, just there. I'm not sure.
Okay, wait.
All right, now I can see you. Only you.
Okay, wait. I stopped the share. I'm going to do it again. There we go. How about that?
Now it's blank, so we'll see if it loads. It's just completely black now.
Yeah, I can see the area of the closed. I can see the paper.
Okay, it must be on the internet then on your end. If other people can see it, your computer might be slow or something happening. I don't know. These are the lovely parts of online instruction. Let me know. Is it okay now?
I can see everything okay.
Okay. If you're having a problem, maybe try try exiting and rejoining the meeting, maybe? I'm not sure. Keep me updated. But I will post it on YouTube if you missed something as well. So I apologize for technical issues, but I'm kind of confined here. So anyway, the area of a closed two-dimensional figure is the amount of surface the shape covers. So again, you want it to be closed. Strictly speaking, you could probably do it not closed. Like, for instance, like the only issue with it not being closed would be like, what would you do here, right? So if I want the area of this shape, right, it's kind of like, how much space does it cover? But if it's not closed, what am I talking about? All of this space? You know, it's like if you ever played around with MS Paint and you tried to use the fill tool and like you had a hole in your shape, it would just fill the entire screen with like red or something. And it's the same kind of idea. If it's not closed, then, and you want to talk about area, it's not really well defined because you're going to be taking the area of like everything, and it's pointless. So when we talk about area, just like with perimeter, we generally talk about a closed two-dimensional solid or two-dimensional like shape, right? So for instance, the area of this shape, obviously, I just mean the area that I'm shading in now, right? Up until the border. I don't want anything out here. I just want how much space is inside of it, right? So for more concrete examples, we can kind of do shapes like this. And again, I did these by hand. I don't know how to make images that well. I mean, I could probably do it if I spent the time working on it, but it's so much quicker to draw them. So I just drew them in here. And so this first example, I made, these first two actually, I drew with blocks to make our lives a little easier. So this first one, I have 1, 2, 3, 4, 5 blocks along the top. It's 5 centimeters. So you can probably figure out that, again, assuming each block is exactly the same, even though my drawing is not, that each block is 1 centimeter by 1 centimeter. And then going down in the vertical, I have 1, 2, 3 blocks. So each block is 1 centimeter by 1 centimeter as well. All right. So if each block is 1 centimeter by 1 centimeter, right? So how much area does each block take up? Haven't really talked about area for any object. It's going to be 1 centimeter squared. So basically the idea is that, so it's a square. And so the area of a square, maybe I'll just give you this on the side. So an S by S square, so is going to be, is S squared. So you just square the sides, or side squared. All right. So for instance, if it's 1 by 1, then the area is 1 squared, which is 1. And then usually what you do is you square the units as well. So inside here is 1 centimeter squared. All right. And it's the same for each. You could write 1 centimeter squared in each block. And so the area taken up is exactly 1 centimeter squared for each little block. All right. So for this rectangle, this chocolate bar, the area is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? 15 centimeters squared.
Can't you just do 5 times 3?
Yes. Yeah. You totally can. But what the fun is that? So the area is 5 times 3. Maybe I should put in the units there. Again, we'll do units more next unit, but I want to do a little bit, right? So to me, 5, this is centimeters, times 3 centimeters. And so it's 15 centimeters squared, right? And so this centimeter square business is just notation, all right? It means that this is an area in units of centimeters. And you can kind of see where this notation comes from, right? I'm multiplying 5 and 3, and that gives me 15. And then I'm also multiplying centimeters by centimeters. And so the natural like unit is to multiply the centimeters together. And obviously that's not a number, it's a unit. So we just write it as centimeters squared, which is literally the same as, it's the same as saying centimeters times centimeters. All right. Does this make sense to anyone? Again, so however you want to think about it, you can think about it as each little block taking up 1 centimeter squared, and then you have 15 blocks, so it takes up 15 centimeters squared. Or you can just think of it as, oh, it's 5 centimeters by 3 centimeters. The area is 15 centimeters squared. Both work. Let's try the next one. Next, we have a triangle. And again, I tried to draw it so that each little block was kind of the same, but again, it's by hand, so what are you gonna do? But what we can do here is this one, I can't just multiply 4 by 4, right? Because it's not a square. It's not a rectangle either. So I can't just multiply the sides to get the area. But I can still count, so let's count. So again, you'll note that each little block, I have 1, 2, 3, and I have like 4 blocks by 4 blocks. Now the end blocks are half, but we'll assume that they're still, like this is still 1 centimeter. So 1 centimeter, 1 centimeter, a lot of space, but 1 centimeter, 1 centimeter. All right, so each of these is 1 centimeter in like length. All right, so each block still takes up 1 centimeter. Each of the whole blocks, right? So I have 1, 2, 3, 4, 5, 6. I have 6 whole blocks. And then half blocks, again, assume everything kind of works. I have 1, 2, 3, 4 half blocks. Right. So for that, how many whole blocks is 4 half blocks?
2.
2, exactly. So this is equal to 6 plus 2 whole blocks, right? And the area of a whole block is 1 centimeter squared. So this is just, so area is 8 centimeters squared, right? So for any shape, really, for any shape, if you took like that squiggle I had on this page over here and you put it on a piece of grid paper, you could find the area by kind of counting the blocks it takes up, right? And if you knew the area of each block, you would then know the area of the shape, vaguely speaking. If it's, the 2 examples we did here, everything is kind of uniform and, everything's kind of nice and straight. But if you, for instance, if you try to do this one and you put it on like a sheet of grid paper, you could still count the number of blocks. You would have to approximate, like, I don't know, like this, like what is that exactly? It's like a little part of a block. It's hard to tell. You could approximate it though, right? And so that is one way you can find areas. You put a grid on it, you measure how much each little block is about, and then that tells you the area. Right?
Sorry.
Yeah.
Can't you just use the formula too? Wouldn't it be like area equals 1/2 base times height?
Exactly. Yeah. That's the way we're going to do it, actually. I just kind of wanted to show you how you could do it really basically without formulas or anything, just by counting, right? But
is that supposed to be inches? Like how each one of those equals 1 centimeter?
It is. Thank you. You know what?
I was like,
just going to do this. I'm just going to change it to centimeters. Sorry about that. That was in centimeter land from the previous problem.
I did the same thing on my paper.
Thanks. Anything else? Is that good? Any other questions? All right. So as was pointed out, this does work, but it's not very efficient. We wanted to find a formula. Here it is too. So we have formulas. So as I said, for a rectangle, it's pretty simple, right? For a rectangle, I have something like this. And it's just so you have, I'll call this the base, this the height. I don't know. People have names for these things. I don't really care. And so the area here is just base times height. Okay. So you just multiply them together. And it's exactly, like the reasoning behind it is exactly the same as in this example here. You're just multiplying the blocks and you get exactly what the area is. And then the units follows. I didn't put units here, so it would be units squared, depending what the units of B and H are. Right? A parallelogram is more interesting. And let's see, so let me draw a parallelogram first. So a parallelogram will look like this. Oops, see, its shapes are hard. There you go. I'll try to make it vaguely straight. Okay. So all the sides should be parallel. So both opposite sides. Parallel. All right, so that's where the name comes from. So these two sides are parallel, and these two sides are parallel. And I didn't define what parallel is. Oh, we did. Maybe we didn't. I talked about perpendicular lines. Parallel lines just mean they have the same slope. So maybe I'll put it down here. We're going to define in our definition. So parallel lines are lines with the same slope. We don't really need to know that. But so it's very much an aside. All right. So a parallelogram, opposite sides of the shape are parallel. Parallel lines mean the slope is the same. So if you were to find the equation of these two lines, you'd find that m for both would be the same. If you found the equation of these two lines, you'd find that m would be the same. Doesn't matter. Anyway, let's see how we can find the area. Now for this, what I'm going to do is I'm going to call this bottom length here the base, or B, and I'm going to put a line. So right at the edge, right at the corner, I'm going to drop a dotted line down. And this is going to be my height, or H. All right, so I did some I don't know, cutting this morning with paper things. And so this is a parallelogram. Let's see if I can get it to where it should be. Nope, where does it go? Ah, like this, there we go. All right, so this is a parallelogram. This is B, the base, or you can put it down here, and this is the height, right? So we want to find the area, and a strategy that you can use to find the area of shapes is if you have it like on a sheet of paper, or if you're thinking about it in like 2D space or on a plane, if I cut the shape and move it around, assuming I don't get rid of any paper, the area is the same, right? Like it doesn't matter if I take this and move it here, like the area of this new shape will be the same as the area of the parallelogram, right? Because I didn't discard any paper. So as long as you don't throw away any paper, when you cut it into pieces, you'll have the same area. Now, the trick that we're gonna do for this one is we're gonna
flip it over and make it a square.
Yeah, rectangle. But exactly, so I cut it along the H, and I'm just gonna move it over here. And now it's a rectangle. And what's the area of this rectangle?
Base times height.
There you go. So the area of this parallelogram is just base times height. Just by that argument. Like, this is your parallelogram. And you just cut it at the H, that dotted line I put in, move that over here. And you'll note that since these two lines are parallel, by definition, like it's a parallelogram, right? So these two sides have to be parallel. So that means I can move it over here. And there won't be any gaps. If they weren't parallel, you might have like some kind of like, might like not meet up. It might look like that almost, and you might have a gap, and it might not work as a rectangle. But since there's gonna be no gaps and they're perfectly parallel, they'll always meet up and it will always be a rectangle. So the area is just B times H. Okay. So any questions there? All right, we're gonna do two more, and then we'll do some examples. But it's kind of fun. I like this part of geometry where you're kind of determining formulas. Right. So for triangles, let's do a right triangle first. So a right triangle is just one with 90 degrees. And I have paper for this. That's very exciting. All right. So for the right triangle, as I said, it just means that this is a big one. Don't worry about it. It just means that there's a 90-degree angle in it. So, or that you can think of it as basically two of the sides meet perpendicular. So like, like this could be like a floor and this could be a wall, and they meet, hopefully, if your house is built well, in 90 degrees, right? All right. Anyway, so this is our shape. I will call this H, and I'll call this B. All right, now, we're gonna do almost the same trick, but it's going to be slightly different. So if I make a copy of this triangle, right, and I put it here. Oh, that's not right. Here. There we go. So it's the same triangle. These two triangles are the same, right? So the area is exactly 2 times the area of one triangle, right?
Would you just do base times height divided by half?
Exactly. Because the area of this is 2 times the area of the triangle, right? Because there's 2 triangles. But the area of this whole thing is just base times height because it makes a rectangle. And so the area of one triangle then is 1/2 base times height. That make sense? So again, we're just duplicating it. So when you duplicate it, you get 2 times the area. And if you can compute that, you can then just divide it by 2. So for instance, what I mean is that the area of 2 triangles is B times H, right? Because it's just a rectangle. So area of one triangle is 1/2 B times H, because you just divide it by 2. And there you go. But it's a neat argument. It's a really nice argument, actually, where you're adding on area to find the area of something smaller. It seems counterintuitive, but it works. So for a right triangle, and again, a right triangle has 90 degrees in one of the corners. I'll call this the height, and this the base. The area is 1/2 base times height. All right, so that's for a right triangle. A right triangle is, they're really nice, actually. And if you do take algebra and trig, you do a lot more with right triangles. Namely, you can kind of define trigonometry based on them. But we have more general triangles because not every triangle has a right angle. So in general, let me get my new shapes. I don't want to separate these. So again, my shapes are wildly different sizes. I based solely on where I got the images from. So here we go. So here's my regular triangle. Not regular, it's just a generic triangle. So here you'll note the triangle doesn't have a right angle, right? This is not 90, this angle's not 90, and this angle's not 90, right? But what I did was I drew a line down, and that gives me the height of the triangle. So I'll label that H, and the base I'll label B, just like before. Right, so that's B, the H is the height. And we want the area of this triangle. And we're gonna do it just like we did the area of the other triangle, but it's cool too. So I made 2 copies of this triangle. So you'll note that if I lay these 2 shapes on top, oops. Right, so I have 2 copies of the triangle on top of each other. So what I'm gonna do is I'm going to take this part and put it there. Oops. And I'm gonna take this little other part and put it there. Right? And now it's a rectangle. Isn't that cool? And you'll note that it's just 2 times the area of the triangle again. Right? So area of 2 rectangles, or sorry, 2 triangles. Let me just write that again. I'll put down here. Area of 2 triangles is, and so again, it's the height is the height of this rectangle that we made, and the base is the base of the rectangle. So the area of 2 triangles, a rectangle, is base times height. And so just like the other triangle we did, the area of 1 triangle is exactly half that. So area of 1 triangle is 1/2 base times height. So it's kind of fun. It has exactly the same formula as the right angle triangle does, but the proof is a little different, right? For the right angle triangle, we didn't have this little smaller triangle on the left. We just had this fatter one on the right here, right? But same argument. It's just a little more complicated. It's not by much. So anyway, for generic, for arbitrary triangle, so it looks, I'll draw it like this. So this is B, that's H. Again, the area is 1/2 BH. So it doesn't matter what triangle you have. If it's a right triangle, if it's a normal, any arbitrary triangle, it doesn't matter. The formula is the same. Just be careful when you figure out what the height is, right? The height on a right triangle is just this side, and the base is the other side. So basically, you're multiplying the two smaller sides together, dividing it by 2. For an arbitrary triangle, you have to drop a line from here down, and that's your height. You compute the height of the triangle. And you'll always be given that height. Like if I ask you to find the height or the area of a triangle, it'll be given. It'll be clear what the H is, clear what the B is. I'm not going to ask you to measure things. It's weird. All right, questions?
So essentially, you're taking the highest point on the triangle and drawing a straight line to make a right angle, and that's your height.
Yep, exactly. Yeah. And again, you won't ever have to draw that yourself. I don't think I've ever had to do it. Like, or I don't think I've ever seen it as an example or an exercise in the textbook. It'll always be labeled. So like, I'll do an example after I finish this trapezoid one, and you'll see what I mean. But yeah, awesome. So, and the last shape we'll do is trapezoids. Let me shovel this away. And a trapezoid looks like this. Eek. So a trapezoid is kind of like a parallelogram, but the two opposite, one pair of opposite sides is not parallel. So like you'll note that this line, the bottom and the top are parallel, but the two sides are not parallel, right? So this side is not parallel to this side. In fact, this has, if you look at this as a line, this has positive slope and this side has negative slope, depending, I guess, how you set up your axes, but we'll assume that they're set up as normal. We want to find the area of this, and I guess I'll just sketch it for you, how you'll find it. I won't show you, it requires a little algebra to get to the answer that the book has. It's not bad, but I don't think it's helpful. So what we do is the same kind of thing, right? What I'm gonna do is, this inside bit is a rectangle. So that we can find the area of kind of easily, right? All we need to know is we need to know this length, I'll call this B1, and we need to know this length here. So, oops, a little over. I'll call that like B2 maybe. Right. Oh, actually that's B1. I'm stupid. That's B1 as well. These two are the same. This length and this length are the same. So this is B1, right, on the top and the bottom. And the height is H again. So the area of this inside rectangle is just H times B1. Fine. Now, the only thing you have to do now is find the area of this triangle and this triangle. But you can do that based on the argument we just did to find the area of triangles, right? It's just 1/2 base times height. The height for both of these triangles is H. And the base, it's not given, but you can label it. So I can put this like, I'll call this, I don't know, I'll call this B3 here. You'll see why in a second. And I'll call this B4. All right. And I'll call this whole thing B2. All right, so I'm labeling a lot, but basically the idea is that I use these same arguments where I copy the triangle on top of it itself. I find the area of this triangle, and then I find the area of this little triangle, and then I just add them all together. I add the area of this triangle plus this rectangle plus this triangle, and that gives me the total area. All right. And again, I won't do the algebra, but that's the idea. You're just doing 3 separate areas and adding them together. And in the end, let me just give you what it looks like. In the end, you end up with something like this. So it looks like this. So I'll call, this is H. I'll say this is B1. And again, this whole bottom part is B2. So the formula that you should get when you add up all these different little sections, you'll get 1/2 H times B1 plus B2. So the area is that. All right. But that's how you find it. All right. And just to be for completion, I'll just show you. So earlier I did it. So as I said, basically you find the area of this little triangle, which I called A1, the area of this rectangle, which I called A2, and the area of this one, little other triangle called A3. You compute all three of them, and then you just add them together. And you do a little algebra to get that formula. And this is the formula you'll find in the book. So that's why I wanted to get that formula. But I mean, these are all valid expressions. Anyway, that's not important. What's important is that you understand how we can use these, and that's what we'll do next. So any questions before we do some examples? All right. Let's see, I'm done with this. Done with you. Here we go. All right. So let's actually do some number stuff. So find the area of the following shapes. So A, this is a triangle, right? And I guess I should note, there you go. Usually you label, it doesn't matter. The implication is that this 3 is the height. And I don't give any units here, so I won't list units. If you're not given units, you don't generally have to list them. So what's the area of this triangle going to be? So remember the formula of a triangle?
1/2 base times height.
Yep. So area of a triangle is 1/2 base times height. So the base here is the bottom, right? Base, bottom. So that's this 10. And the height is how high the triangle is. So that's 3 here. So it's just going to be 1/2. Yeah. Sorry?
The area is 15.
There you go. Yep. Because it's 1/2, 10 times 3. So it's just 15. Right? 30 times 1/2 is 15. And again, no units are given, so don't worry about it. All right. So that is a triangle. 2, or B, sorry. This is, and I guess you do want to be careful identifying what shape you're dealing with, right? So a triangle is really easy to spot. It's got 3 sides. But this might not be as easy, but you'll note that 2 sides are parallel and 2 sides are not parallel. So it's trapezoid. And then for C, you'll note that 2 sides are parallel, 2 other sides are parallel, so it's a parallelogram. But this one's a trapezoid. So we said that the area of a trapezoid, is 1/2, I'm kind of out of space here, 1/2 H B1 plus B2, right? So B1 is the, at least the way I gave it earlier, was the height, or the length of the top, and the B2 was the length of the bottom. So here it's flipped on its side, but if you just rotate it, you'll see that this is your B2 and this is your B1. It doesn't actually matter which is which, right? The only important thing is that B1 and B2 are the lengths of the parallel sides. So you don't want to use this part and this length as your bases because those aren't parallel. But these two ones are. So it's just going to be 1/2. Your height is 2, and then your base is added together. So 3 plus 5. So what is that? 2 divided by 2 is 1, so that's negligible. And then you just get 8. Oh, and you do have units here, inches, so it's inches squared. All right. Any questions with that one? I think trapezoids is the weirdest shape. I don't know why they're a thing. All right, so the parallelogram. Again, as I said, if you're given the parallelogram and asked to find the area, it will most likely be given to you looking like this. Same with a triangle. It will usually be given to you looking something like that, unless it's a really tricky problem. But like here, so for instance, this is your base, and then your height is just how high it is, right? Usually it's a dotted line, or it could be a straight line like I had for the triangle, but that's your age. And then you just go back. Let's see if I find it. Just go back to where we did it. What are we doing? Ah, here. And remember, for the parallelogram, there's no 1/2 because you just take this like little triangle and move it over there, and it makes a rectangle. So it's just base times height. So this one is just, so area of parallelogram is base times height. So it's just 14 times 12 millimeters squared. What is 14 times 12? $168. So 168 millimeters squared. All right, so those are the three hardest ones. Obviously, squares and rectangles is just base times height or side times side. So those, not an issue, but just make sure you identify what kind of shape you're working with. And you could even be doing combinations of shapes, right? You could, well, we'll do an example like that after. But anyway, let's do one more of these. So what's the area of this rectangle?
Well, one area is base times height, then 1 times 10 is 10.
Exactly. 1 times 10, so it's 10. And then what are my units going to be?
Yards.
Yards squared, right? So whenever you're doing area, you put a squared on your units. All right. Anything there? All right, so let me do an example like I just mentioned. So what if I had like a house? Ooh, and what if I didn't have a front door? Let me do All right, so I have a house, no front door. And then let's say this distance is 2 feet. Let's say this is 6 feet. Let's say both of these are 4 feet. All right, and then what else? Oh, and then this. Oh, and we need this too. So let's say this is 2 feet. No, 3 feet. All right, and then one more. Let's put a, do we need anything else? Oh yeah, we need this height here. Let's say this is 4 feet. All right. It's a very convoluted example, but we'll figure it out. So let's find the area of this shape, the entire thing, like this entire front of a house, right? I think we've all the measurements we need. All right, so what we're gonna do is we're gonna break it into pieces. So like what I was saying earlier is like you can always take a complex object and try to break it down into smaller, more simple objects, find the area of those using known formulas like triangle, rectangle, square, trapezoid, yada, yada, and then just add them all together, because assuming you don't throw away any paper when you cut it into pieces, it's gonna be the same area. So like here, for instance, I already kind of cut it in pieces. Like we have 2 triangles in the top, right? And these are gonna be right triangles. So we can compute those areas. And let's suppose it's perfectly centered over this door. And then in the bottom, we have a bunch of tiny little rectangles, right? So what I can do is I can break it into 3 rectangles. I can continue this line across, and I can continue going over there. So you can think of it like if you have like those blocks, like my nephew plays with these wooden blocks, and you can kind of break it into components that look like those colored little wooden blocks that kids play with. And then if you know the area of each of the smaller, simpler blocks, you're good. So for instance, we have 1, 2, 3, 4, 5 blocks, and we just need to find the area of each and then add it together. So what is the area of this and this rectangle? So they'll have the same area, right? Because they have the same dimensions, 4 by 6. And then
I was going to say 10.
Oh, careful. So you don't want to, so if you add them, that gives me this length, right? It gives me the length from on this side and the bottom. So you're giving me like half the perimeter, but I want the area.
Oh, okay.
So instead of adding, what do I do to find the area?
4 times 6
multiply.
is
Yep.
24 squared.
Yay, exactly. Yep, you multiply them. So it's going to be 24 feet squared. And then the same for this one over here.
I should have said.
That's okay. You're in the right track. So these both of these little blocks have 24 feet squared. What about this kind of cornerstone block? What's the area of that one going to be? So it's 2 by 3 feet. So what's the area?
2 by 3 feet. Wouldn't it be the 4?
Oh, I'm sorry. You're right. Sorry. You good point. So it's going to be this length. This little bit's 3 feet. I was reading my sketching correctly. So it's going to be 4 plus 3 plus 4, right? This entire gap.
So it's 11 times 2. Which is
Exactly.
22 feet squared.
Yep. So this rectangular block at the top is 22 feet squared just because it's 4, 4, and 3. So this entire length is 11, not 3, like I said. All right, and then the top, so let's assume that our house is symmetric. So that means that this is half of 11. So it's 5.5 and then 5.5 feet. So you might need a calculator. But remember the area of a triangle with height 4. Oh, I guess you can do it 2 ways. So the one way you can do it is the way I was going to do it, is compute the area of both of these smaller triangles, right? Or you can consider it to be one big triangle like this, right? So if you look at it like a big triangle, the base is 11 because it's the same as this length, and then the height is 4. So it's just 1/2
Feet squared.
Yep. So base was 11, 4, so 22 feet squared. Cool. And so the total area, as I said, we just add all these smaller areas together. So I'll put it above maybe. So total area is, so it's 22, the top triangle piece. 20, I'll put feet squared maybe. And then we got this like support piece. It looks like an I-beam. Again, also 22 for some reason. Right? And we have 2 feet. So plus 24, plus 24. And you just add all this together. So what is that? 22 plus 22 is 44, and then 48. So it's 92 feet squared. So there you go. And so like if you've ever been painting or tiling a bathroom or something, and you know if you have a bathroom and maybe your walls are rectangle, but maybe you're not tiling behind like a sink or a toilet or something, you might literally have to do something like this, right? You might draw a little diagram. You might be like, oh, I'm not going to do behind the vanity. So I kind of cut that out on my diagram. And then you say, oh, I'm not going to do behind the toilet maybe. And then you cut that out on your diagram. And you have like this kind of weird shape with these missing pieces. And so to find the area that you need for tiling, to buy your tiles, you then maybe just break into pieces, compute the smaller areas, and get an estimate. Right? So this is like realistically something you could be doing if you were redoing like a bathroom or like a kitchen or something. Right? I just did this actually for my parents' bathroom, but that's besides the point. Any questions about this example or the other ones about an area? All right, so again, very practical actually, if you do anything remotely close to home improvement. But move on. We're just gonna end with this today.
I just have a
yeah.
quick question for you.
Of course.
Now, is this something new that people have been teaching? Because I never went through all this in like grade school or high school where they really broke those down like that.
Oh.
I noticed, because you did that in the last time I took the class.
Yeah.
And I'm like, is that a new teaching technique?
I don't think so. I don't know. The only reason I like to do them is because it's a little more creative than like, so like you can do like examples like this all day where you have, I give you like a triangle and I give you like a square or something like that. And these are good to practice with the formulas, but I like those examples because they are a little more, you have to do a little more work, right? You have to break this more complex object down into component shapes. And I don't know, I find them a little more entertaining. Yeah, no worries.
I was in school, they broke it down like that too.
Yeah. I think it's a thing. Anyway, the last thing we'll do today, just a little triangle. As I said, we're not going to do anything with trig, so don't worry. But we're just going to do a little bit with the Pythagorean theorem. So a triangle, as we've said repeatedly, is a 3-sided polygon. When 2 sides of a triangle meet at a right angle, we call it a right triangle. So we've already been using this kind of implicitly. For a right triangle, and this is the thing we're going to do, we have the Pythagorean theorem. and I think everyone has seen this at some point in their life. But so let me draw a right triangle. So it's right again in the sense that you have 90 degrees, and I don't know, I'll call it A, B, and C. So the C is going to be the hypotenuse. So that's the longest side. And so the hypotenuse will always be opposite the 90 degrees, right? So for when you have a triangle, if you add up the degrees in the corners of the triangle, it's going to be 180. So if one of them is 90, the other two have to be strictly smaller than 90, right? Because they can't be 0. So this 90 is necessarily going to be the longest or the biggest degree. And so the side opposite it, and this is something that you learn in geometry in high school. We're not going to cover it here. But the side opposite, yeah?
When we were in high school, is this SOHCAHTOA? Sine, cosine, and tangent?
We're not going to do that, but yeah, it's related to that vaguely, the different sides. Yeah. No trig. Don't worry. We're not doing any trig. But it just kind of touches on it a little bit. But as I was saying, so the side, you always know the hypotenuse because it's the longest side. Alternatively, it's the side opposite the 90 degrees because the degree corresponds to the length of the opposite side. Doesn't matter. Anyway, just know it's the longest side. So the theorem is that the two smaller sides added together equals the bigger side squared. Right? And so this allows us to find missing sides of some right triangles, all right triangles, I guess. But so for instance, for example, we'll call it A. So if I have, and it only works for right triangles. Don't try to use it for normal triangles. It won't work. But if I do like 3 and 5, maybe I'll call this side B. So what is B? Right. So again, you'll note it's a right triangle. So I can apply the Pythagorean theorem. And then what you do is you find the hypotenuse. Hypotenuse is going to be, as I said, the side opposite the 90 degrees. So that's my C. That's my A. The labels don't really matter. The only thing, especially the B and the A, can be flip-flopped. They're just the two smaller side. The only thing that's important is that you identify C with the hypotenuse. That's the only thing. So, so as I said, 5. So I just plug it in. So 3 squared plus B squared equals 5 squared. And now it just requires a little bit of algebra to find the remaining side. But, you know, I want to find B. So I bring everything that doesn't have a B in it to the opposite side. So I'll subtract 9 from both sides. So I get B squared equals 5 squared minus 3 squared. 5 squared is 25. 3 squared is 9. So 25 minus 9 is 16. So I get B squared equals 16. So what is B if B squared is 16? Trees are falling. What can B be? Any ideas?
4.
8.
4. All right, so what you do is you take the square root. So it's gonna be the square root of 16. So be careful when you do that. So so maybe I'll do it on a separate sheet of paper, but so note. I think we'd mentioned this when we talk about exponentials, but B squared equals 16. So what this means, the squared, it means that B times B equals 16. So you're looking for a number that you multiply by itself to get 16. So that's 4. It could also be minus 4, but we don't count not minus 4 as an answer because negatives don't make sense in our case, because what is a negative length, right? It doesn't work for us. So we just take the positive one. But so B equals 4. So it equals this radical 16 square root. And so on your calculator, you know, so if you're unfamiliar with square roots, hopefully you remember it a little bit. Why can't I get this? There we go. There we go. So it's going to be, in this kind of calculator, it's down here. It's right above the x squared is like a little blue. So you do second x squared. And then you put in 16. You get 4. Right? On the other calculator, And again, some of these you would just know, like the square root of 16 you could guess. But anyway, the second one, it's actually similar. It's second x squared there, and then it'll be 16 as well. All right, and you get 4. So either way, if it's more complicated, you might need a calculator. But 16, you could also guess. Questions? Concerns? Issues? All right, I think we will end it there for today. So today's Tuesday. Thursday, don't forget, or Friday, the population project's due. However you want to finish it, I put the doc on there so you can do it on your computer. You can print it, do it on the sheet of paper. You can do it on a separate sheet of paper. As long as you just email some version of it to me, that'd be fine by Friday. But if you don't have any questions, I think we'll be good. And I'll see you Thursday. Good luck.